Welcome. As a psychiatry resident, pretty much your entire future practice is going to revolve around what happens in a tiny, microscopic gap between two neurons. So today, we're going to break down that fundamental unit, the synapse. This is the primary target for nearly all of psychiatric medicine.
All right, so here's our game plan for this explainer. We're going to start with the absolute basics of what a synapse is. Then we'll get under the hood and see exactly how it fires. After that, we'll learn to speak its language, the difference between go and stop signals. And this is the most important part, we'll connect all of that bench science to your actual clinic before we take a little peek into the future.
Okay, first things first, let's build our foundation. Everything we do in psychopharmacology, literally everything, is built on the principles of the chemical synapse. So, what exactly is it, and why is it so ridiculously critical for everything the brain does?
So, the main takeaway here is that we're not talking about a simple wire connecting two points. Not at all. Think of it more like a highly sophisticated processing hub. The keywords on this slide are regulated and monodirectional. This is where the brain's incredible complexity and, crucially, our ability to intervene with medicine truly begins.
Now, what's really fascinating here is the trade-off. You see it right there. Chemical synapses are slower, but they sacrifice that raw speed for incredible regulatory control. That little delay, that chemical step, well, that's the entire basis for psychopharmacology. It creates a space, a pause, where medications can jump in and change the signal. All right, let's dive into the mechanics of this. How does an electrical signal in one neuron actually get across that gap to influence the next one? It's really a beautifully orchestrated process when you break it down.
Okay, so think of this as a super precise 5-step relay race. It all starts with an electrical signal, the action potential, that zips down to the end of the neuron. That jolt of electricity opens up these tiny gates for calcium. Now, calcium rushing in, that's the key. That's the trigger that tells the little bubbles filled with neurotransmitters to go to the edge and release their contents into the gap. That's where drugs like gabapentin work, by the way, messing with these very calcium channels. Finally, those neurotransmitters float across the gap and deliver their message by locking into receptors on the next neuron. And boom, message delivered.
In this number, this just drives home the insane scale we're talking about. This isn't a simple one-to-one phone call. A single neuron is like a ridiculously powerful microcomputer, and it's constantly listening to and adding up signals from literally tens of thousands of other cells to decide if it's going to fire or stay quiet.
So now that we know how the message gets sent, let's talk about what the message is actually saying. At its very core, all this complex neurocommunication is really just a constant push and pull, a delicate balance between two opposing forces.
Honestly, the entire language of the brain boils down to this balance. Excitatory signals are the go signals. They push the next neuron closer to firing. Inhibitory signals are the stop signals. They tell it to calm down and make it harder to fire. When this balance gets thrown off, that's where pathology begins. Way too much go can lead to things like seizures. Not enough stop can show up as anxiety.
And this idea of summation, this is why the brain is so much more than just a simple reflex machine. Remember that neuron with its 100,000 inputs? Well, it's constantly doing math. It's adding up all the go signals and subtracting all the stop signals over both space and time. It's this integration, this decision, that allows for everything from abstract thought to complex emotions. Okay, this is it. This is where we connect the dots from the lab bench to the hospital bedside. Those abstract ideas of go and stop become very, very real when we look at the specific molecules you'll be targeting in your clinic every single day.
Think of this table as your high-level map, your cast of characters. You've got the monoamines, like dopamine and serotonin. Those are the celebrities, central to mood and psychosis. But you can't forget the real workhorses. Glutamate, which is the main go signal in the brain, and GABA, the main stop signal. GABA is what drugs like benzodiazepines target.
So let's look at the manufacturing process for a second. For dopamine and noradrenaline, which are the key players in things like psychosis and ADHD, it all starts with a simple amino acid you get from food, tyrosine. But the most important step, the one that controls the entire assembly line, is this enzyme, tyrosine hydroxylase. It's the main valve. And understanding this helps you grasp why a drug that hits dopamine, like an antipsychotic, can also have downstream effects on noradrenaline.
And next up, of course, is serotonin, the molecule at the heart of most of our antidepressant treatments. This whole process starts with tryptophan. Yep, the stuff you hear about in Turkey at Thanksgiving. The key choke point here is tryptophan hydroxylase.
And here's a crucial clinical point. When you prescribe an SSRI, you're not making more serotonin. You're blocking its cleanup crew, its reuptake, which makes the serotonin that's already been made through this very pathway hang out in the synapse for longer.
Now, these last two are just as critical. Check out GABA, the brain's main stop signal, its primary brake pedal. It's actually made from glutamate, the brain's main go signal, its accelerator. How cool is that? It's just this incredibly elegant bit of biological engineering, turning the accelerator into the brake with one single enzyme. And then you have acetylcholine, which is vital for memory. This is exactly why when you prescribe a drug with strong anticholinergic side effects, you have to warn patients about brain fog or confusion. You're directly interfering with this very pathway.
So finally, let's look ahead. I mean, the synapse is far from a solved problem. It is constantly revealing new secrets, and with those secrets come brand new avenues for treatment. Treatments that are absolutely going to shape your careers.
One of the most exciting new frontiers involves a class of molecules called trace amines. For the longest time, nobody really knew what these did, but we're now starting to realize they have their own unique signaling systems that could be incredibly powerful new targets for drugs.
And this is where it gets really, really exciting. This isn't just theory. We're starting to move beyond just dopamine and serotonin. Targeting these brand new receptors, these TARs, might offer a completely different way to treat something like schizophrenia, maybe even without the same side effects of our current meds. This is the future happening right now.
So, if there's one thing I want you to take away from all this, it's that this fundamental science is not a history lesson. It's a dynamic, evolving field. What we've covered today is the foundation for sure, but the future of your practice in psychiatry is going to be built on the discoveries that we are making about this incredible little space, the synapse, right now.